All right, so let's start our class today. Okay, so this is lecture 3, and today we will focus on image features. And especially we will discuss on these two techniques called HOP and SIFT. So previously we discussed about Jones algorithms, right? Face detection using Jones algorithms. And there are two things that are very important in these algorithms. What are these two? There are two things that are very important, very basic in Jones algorithms. What are those two? Anyone? One is feature extraction. And the other one is what? The second one is adabus, classification. So this is two very basic modules in Jones algorithms, but also in computer vision or machine learning in general. So if you learn about machine learning, even machine learning, which is a wider field in computer vision, so computer vision is part of machine learning, they still have these two components, feature extraction and classification. So this is really, really basic. And even these are used also for deep learning. So if you learn about deep learning, you always have these two things, feature extraction and classification. And in Jones algorithms, what are the feature extraction that we used? What are the techniques that we use? It's called hard-like features. Classification here is adabus. Now, why this works? Why Jones works? One of the reasons, or one of the actually the main reasons, is because of these features. We thought these hard-like features in the first place. Right? So now, why these hard-like features are important? What are the information there that makes this work, that makes the face detection, object detection works using hard-like features? What are the most important things in hard-like features that make this algorithm works? Anyone? Why hard-like features work for face detection? Exactly, edges, and then corners, right? So edges and corners will capture any features that you have in your face, not only in the large scale, because we upscale the filters, right? Not only in the large scale, but also in the small scale, because we have small mask, we have medium mask, we have large mask. And that's the reason, because we want to find features of your face in any different scale. So for example, if we have a mole here, for example, that will be small scale, and that can be captured by small scale mask, a smaller mask. But if you have a larger features like nose, for example, then it will be captured by larger mask. But the basic idea of the mask, as you can see in the Villa-Jones, is basically very simple, black and white. And this black and white is actually -1 and +1. You do the convolution with -1 and +1. And this +1 and -1 will give you edges, most of them, because we have type 1 and type 2, which most likely edges. And type 3, which is a rectangular, you remember type 3 is something like this, right? Type 3 hard-like features look like this. And this one is most likely corners. I do not know, but you can try yourself and do the convolution using these filters and see what happens. See what you can see there. But I think this some of them will give you some corners. So that makes these features, like features, works for faces, because faces is corners and edges in different direction, especially the horizontal direction and the vertical direction. Right. But who created this? Who created these features? Yes, Har, exactly. The person called Har. Right? There is a person called Har, actually, and that one invented the whole configuration of Har features. But Villa-Jones didn't use all of them. They just used 3 of them. And that's why it's called Har-like, because it's not fully Har. Okay? And Har, as you can see, is the name of a person. It means that the creation of these features are man-made, created by Har. And that make a difference between traditional approach. This one, Villa-Jones, is a traditional approach, non-deep learning approach, from deep learning. In deep learning, humans are not involved in the creation of the features. In deep learning, everything is automatically done. So that's why deep learning is very powerful. So deep learning is powerful. It's not because of the classification. Classification, if you have a proper features, right, correct features, and you compare deep learning with SVM, for example, the performance will not be that much different. The things that make deep learning is powerful because this feature are extracted automatically from your data. Okay, so that is the real reason why deep learning works. Any questions here? But again, in deep learning, you always have these 2 kind of modules. One is dedicated for feature extraction, and the other is dedicated for classification. I'm not really sure how many of you know about deep learning. Can you raise your hand if you know somehow deep learning concepts? Don't be shy. I know that many of you already know deep learning. Right. Maybe if you're honest, the number here is only half of the class. And that's something, if you don't know about deep learning, I really encourage you to learn about deep learning, because nowadays everything is deep learning. Okay. So if you want to go into this industry, to go to this path of AI, deep learning is a must. So I really encourage you to learn deep learning. Anyway, so that's the power of deep learning, that everything can be automatically extracted. But the problem with deep learning is that sometimes we do not know, because everything is a black box now, right? From input is you just get the output without knowing what kind of features you have. You don't have any control on the features. That's something that becomes the weakness of deep learning, because we do not know exactly what the feature they use. And in this course, we want to know what are the features, what are the possible features, especially for images. And we know that one of them that can be powerful is hard-like features, especially for faces. And we know the concept already, right? How this feature is extracted. Now, there are many, many different features, but there are 2 most famous ones. One is called Hawk, and the other is called SIFT. Especially SIFT. SIFT is very famous. Before deep learning era, SIFT is the most popular features in computer vision. Hawk is very famous as well, but not as famous as SIFT. We will see later on why SIFT is so powerful. There are a lot of things in SIFT. In Hawk gives you some basic fundamental knowledge before understanding SIFT. Okay. Hawk stands for histogram of oriented gradient. So that's the longer version of Hawk. And there are many different things here. We have gradients, we have orientation, and we have histogram. So in Hawk, there are these three basic concepts. So we have gradient, orientation, and histogram. So first of all, let's learn about gradients. When we say gradient, what is another name of gradient in mathematics? Gradient is equals to derivative. In mathematics, it's more known as derivative. So if you have to define image derivative or gradient, then we have to write it in a vector. So gradient is actually a vector. If it is two-dimensional, then it will be a vector. And because we are dealing with images, then our data is two-dimensional. And if it is two-dimensional, then we have a vector. So the derivative here is dx or di, dx, di, dy. So this is the gradients. It's a vector. So what is di, dx then? What is the definition of di, dx? In discrete, I know that if it's analog, then you have to use limit theory, right? But if it's discrete, what is the definition of di, dx? So to be complete, I have to write x, y there. So what is the definition of this in discrete? I x plus 1, comma y minus I x, y. That's the definition of derivative in the x direction. So for y direction is the same thing. I x, y plus 1 minus I x, y. There are many different variations of this derivative definition, but this is the easiest one. Okay, so if you look at this definition, here, for example, the x definition, in the x direction definition, and of course you can do this in your program, in your programming, right? In your code, you can do this easily. But if you use a convolution, operation, what mask that you have to use? How you define your mask then? What is the dimensionality of your mask? 1 by 2, exactly, 1 by 2. And what is the value then? Right, this, this one, x plus 1, comma y have to be positive. So this one is a positive one, because that one is x, and this one is x plus 1, right? And the other one is x and y, and in this case it's negative. So this one is negative 1. So that's, if you want to do the convolution, then that's the operation for gradients. So in this case, your mask will look like this one. And that's exactly what hard-like features mask look like. right? So the first type of the hard-like features is usually gradient. Gradient in X direction and gradient in the Y direction. Any questions so far? If you don't understand, please ask, because this is very important. That's why convolution is powerful, because it can give you mathematical definition of gradients. But it's not only give you definition of gradients or derivative, but it also can give you edges, and you use a Sobel kernels for the mask. It can also give you blurry output if you convolve with a Gaussian kernel. So convolution, depending on the kernels, can give you many different options, many different mathematical operations. And that's why, again, CNN, which is part of deep learning, is very important, because CNN have the mask automatically extracted or automatically estimated. But anyway, if you don't know deep learning, is fine. Just try to understand that the gradients here can be done using convolution, can be computed using convolution. That's the definition of gradients. Now, that's number one. Number two is orientation. What does it mean by orientation? Oriented gradients. The gradients orientation. So previously we have that vector, the gradient vector, which is di, dx, di, dy. So this is a vector, right? What is the property of a vector? There are two properties of a vector, right? What are these two properties of a vector? It has a magnitude and it has orientation. Exactly. So we are talking about two things here. Because it's a vector, there are two types of a vector. One is orientation, and the other one is magnitude. Now, if you want to know the orientation of a vector, how can you get this orientation of a vector? How can we get the orientation of vector, which is theta, for example? How can we get theta from a vector? Is using not sine, the other one, arctangent. Yes. So if it is tangent, then tangent of theta equals to what? Di divided by di dx. So you can shorten this. This one is y ix. Any questions so far for this orientation? Okay, in other words, as mentioned, theta is the arcus tangent tan inverse of iy ix. Okay, so that's the orientation. How about the magnitude then? How can we know the magnitude? Say the magnitude is m. What is m then? Anyone? What is the magnitude definition? Square root of I y square plus x square. Yeah, that's magnitude. So having the gradients from each pixels, then you will have the magnitude and the orientation for each pixels. And what we want here, theta, is actually from 0. It should be from 0. So theta here from 0 to 360 degree. But if you use tangent, what is the range of tangent? Minus 90 up to positive 90, which is 180, right? So now how we can get the 0 to 360 then? we have to, yes, so basically we have to keep the sign. You have to know the sign, because if the sign is, you have to put the, so I can use this one, the absolute value, right? Once I have the absolute value, then I have to remember the sign of the ix and iy. Now, if ix and iy are put positive, it should be in the first quadrant. If, so this one is y, this one is x. If iy is negative and ix is positive, then it has to be in the second quadrant. Here, should be here. If both are negative, then it will be in the third quadrant. And if x is positive but y is negative, then it will be in the fourth quadrant. So you have all the value from 0 to 360. Is it understandable? You have to keep the signs to know which quadrant the vectors pointing to. Any questions here so far to get the value of the orientation and the magnitude? Again, the value of the magnitude and orientation you will get for every pixels. All right. So if there is no question, so that's all for the oriented gradients. Now the third one is histogram. So in order to get the histogram, first of all, we have to use block operation, block or patch operation. What is meant by that is that if you have an input image, so this one is your input image, you need to, in Hawk, you need to split this into a grid. So the size of the grid, the size of the cell for each in the grid is up to you to define. So let's assume that is the grid, the patch. So in this patch, let's assume that you have 16 by 16. Okay, so 16 by 16 patch. In other words, how many pixels do you have in this patch? Yeah, many, right? 100 something, 300 something. Now, because you have many pixels, you will have many orientation and many gradient, or many orientation and many magnitude for each pixels, 16 by 16 pixels. So because you have many pixels, then you can create a histogram. In this histogram, the bin, the x-axis, indicating the orientation. So this one is theta. And of course, histogram is a discrete. So we can have discrete value there, 0 degree, 45 degree, and then 90 degree, and so on. So it's 45, the rate, the width of the bin is 45 degree. So you can have until 315 like this. Now, if your pixels falls into the range of 0 to 45, then you keep that counting here. So for the second pixels also fall into this orientation, for example, then you add. Okay, so that's called histogram, basically. Right? So in the end, depending on the characteristic of your pixels, they have different orientation, different magnitude, especially the different orientation, they will have this kind of profile. I'm not really sure, but you can imagine that it's just an example there. So this is called histogram of oriented gradients. But in this histogram, we don't really use the weight. We don't really use the magnitude. So where is the magnitude here, right? So the magnitude is actually when you add one value here. Previously, I just mentioned if it is 1 pixel fall into that range, you add 1, right? But that's not the case. You should multiply that with the magnitude. So this is weighted histogram. So for example, if the magnitude is 0.5, for example, then it's not 1 here, but it's 0.5. So you add based on the magnitude. Any questions here? So if you draw this histogram in arrows, right? The arrows referring to the direction. Then for that 16 by 16, you will have a very different, arrows there. The arrows is actually representing the magnitude of each bin. So you can put this one, actually, if you want, you can put this one on top of that. Then will give you, that patch will give you the orientation, dominant orientation of the pixels in that patch. Any questions here? Well, this operation is not necessary. It is only for visualization, basically, right? The most important thing is that this number here. So this is the features. The whole things here, the whole things that we have here is called features, Hawk features. The features is in terms of histogram. So now, if we have features, what is the next thing that we need to do? What kind of next thing that we have to have? Is we have to have, after we get features, the next one is, sorry again, not classifier, is that too far? We are descriptors. So remember that features is just a concept. If you have to put it into a number, which is called feature factors, right? You have to transform this into called descriptors. And descriptors have another name, which is called feature factors. And in this case, for 16 by 16, in this case, for example, 16 by 16 patch, what is the length of your descriptors? What will be the length of your descriptors for 16 by 16 patch? How many numbers in your features? The numbers will be 8. The number will be 8 numbers. Because these 8 numbers refers to 8 bins. So this value here, the value 2 or whatever the number there, is basically the number in your descriptors. Any questions here? Okay. Yes.
What was the angle of description because it was situated in
Which one is continuous? The y-axis, you mean?
No.
Yeah, the bin is discrete. This one is discrete. So here is discrete.
What is the angle?
That's the angle, the orientation, theta. It's non-discrete. Yeah, it's a range. So one bin, for example, 0 to 45, and your angle is actually 10 or 10.5, for example. Then that still fall into the bin 0 to 45. Yeah. Yeah, good questions. I didn't explain that in that details. Any other questions? If you don't understand, please ask. Yes. Why this is 8? That's a good question. So again, this is defined by the inventor of Hawk. They just use 45 orientations later on, I will give you the intuition what is the meaning of this histogram or orientation of the arrows for human detection. So this hawk is very good for the application of this. It's actually the application is actually human detection. So yeah, I will explain later on why this is useful for human detection and why 8 directions is enough. Basically, this is 8 direction, right? On that direction, what is that? I don't know, east or west or whatever, right? That's if it is east, then there is a west there, and then the north there, south there, and so on. So this 8 direction that the inventor of hawk thought about. Yes.
We talk about this situation in terms of this 50 by 50 match. And we know that the descriptor is derived by a whole in.
That's right. So yeah, that I will continue that one. I haven't get into that point. So just for now, just assume that you have a 16 by 16 part of the whole image, small patch, and that for that small patch, we will have a descriptor with a length of 8. For that 16 by 16, we will have a vector with the length of 8. Yes.
Would you also quantify the value of y-axis?
Yes. So the y-axis is actually the value. So if you have a vector here, so this vector is actually 8 pin, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, right? So for example, for the first pin here, what do you want? What is the value of y-axis you want? For example, 2.5. So you just put 2.5 there. So for the second pin, maybe 7.3. So you put 7.3. Right? So that's the histogram that you will have. Sorry, the factor that you will have. Any other question? Yeah, this is a good question because I didn't explain that. Yes.
What about the edges? How do we process the edges?
Edges of what?
Pixels on the edges.
Oh yeah, we don't care as usual. When you do the convolution, we always ignore the edges because in image, edges doesn't really have much information. Or if you ignore 1 pixels on that edge, you will be okay because normally the information is beyond 1 pixels. All right. Any other questions? Yes. No overlap. Yes, a good question. There's no overlap. So as you can see there, there's no overlap. We just put a grid there. Any other question? Yes. Yeah. So actually, I already asked for this one, for this application, for human detection, actually 8 pins will be enough. But of course, you can create more dense. So if you create more dense, then it will be like this. Whether this is necessary or not, of course, it really depends on your application. Whether you need to really have that information of gradients in such a detail. But let's stick with, if you don't understand this, let's stick with 8 first, because 8 is actually already informative for human detection. If it is 45 by 45, you mean? 45 that's already up to you. Whether you want to include in the boundary is really up to you to decide. As long as you're consistent, it's fine. Any other questions? Okay. If there is no questions, then let's move on. So this one is again is only for 16 by 16. Of course, you can put it 20 by 20, 40 by 40, and so on. But the length of the descriptor will still 8. Regardless the size of your patch, the length of your descriptor for that patch is 8. Okay. Now, you have to do this for all blocks, for all patches. So you have to do this for this patch, for this patch, for this patch, and basically all the patch. So you have to have for all patches, and each patch has the length of 8. So assume that you have 10K, assume you have 10K patches, 10K patches, 10,000 patches. What will be the length of your descriptors for that image, for the whole image? It will be 80K. The length of your descriptor will be 80K because you concatenate every patch with each other. So for the whole image, you will have a factor with a length of 80K if you have 10K patches. Okay, so any questions here? So that's all it is, yes. That's right. I didn't explain that one. But for this one, the kernel size is static. It's only 1 by 2. It's only gradient for pixel level gradients size. Yes, it doesn't change. It doesn't. It's not really like highlight features. Yeah, good questions. Any other questions? Right. So I will show you so this one is if you have an image of a person, that one, for example, and then you compute your hog. For each patch, your hog will give you the orientation of the arrows there. The brighter the arrows means that the magnitude is higher. The dimmer the orientation or black, it means that there's no orientation in that direction. That's for the middle one. If you visualize in this way, that's the visualization that you will have. Right? And if you remove all the arrows, all the orientations, and only focus on the dominant one, only focus on the most dominant one, then this one, the most bright picture that you will get. Okay, so is that become intuitive now? What is the use of this? What is the use of this hog features? To extract. What kind of extraction of information that we get from hog? Edges, yes, the contour of the body of the person. And of course, the person can have clothes like what I wear today, right? Many texture. And if I'm the person there, the histogram will show all my shirt's texture. But we have to do this not only for me, but for many people standing, not sitting, not sleeping, but standing at the same kind of location in the middle of the image. If you have that kind of data, for my data, because my clothes, then there's some texture in the middle. But for many other people, it will not be consistent. So it will be removed anyway when you do the training. And because the most consistent orientation of the contour will be my body contour for human contour, that's how we can get the information of human being. Any questions here? Okay, so again, this one is only for our visualization. It's really not used in the algorithms. The algorithms will only consider the numbers in the feature vectors. So this number, then 80K, if it is 10K patches, the 80K for one person, and if you have 50,000 person, then you will have 50,000 vectors. All right. And the next step is the same as in Viala-Jones algorithms. Then you have to use a classifier to learn the classification between human being and non-human being. Right. Any questions? It's very simple, I think. Okay, so if there is no question, let's move on. So this is called hog. So we're done with this. So the second features is called SIFT. So the second features is this SIFT features. How many of you heard about SIFT before? One, only one, two, three. Okay, very few of you. Okay, anyway, so I will explain SIFT as little as I can. Right. So there's a lot of mathematics here, so be prepared. Okay, anyway, so let's start from the beginning. Okay, so the basic idea of SIFT is basically for image matching. So what does it mean by image matching? Image matching is something that you can see here. On the top and at the bottom, you have two images. And we know for human, they are taken from the same scene, the same mountain. Now, our task is to match them where the location of these two images that are overlap. That's called image matching or alignment or registration. So image matching, registration, alignments are all the same thing. Basically, you try to match as much as you can two different images. So now, if you have to do the image matching, how can we do this, right? Automatically. That's the question that we want to answer in this exercise. The problem is that image matching is very, very difficult. It's still an open problem even up to now. Why it is difficult? One of the reasons because of this, the orientation are different, right? If it is the orientation or perspective are different, it's very difficult to match or to find the overlapping regions. So that is the problem of perspective. And right, so in these techniques, SIFT can be useful because SIFT can give you key points. So the dots, the white dots here are called key points. So we will try to find these key points. And these key points have to be unique or have to be consistent for the left image and on the right image. If they're not consistent, you will get a wrong matching, right? They have to be consistent. If the top is the key point, so for example, key point A is at the top, then the same key point A prime have to be found at the same place. So then you can match A and A prime. Okay, so again, the key point A here have to be found consistently in both images. And once we have this unique and consistent key points, we want to match them. Oh, by the way, you have to pay attention on this because this is your assignment. So this is the starting point of your assignment. Okay, so you have to use SIFT and then you have to do this operation, matching key points. So you use a matching of the key points, and once you match the key points, then you can have the overlap between the two images. And this is useful for this purpose here, for having panoramic images or mosaicing or image stitching. So this one is useful for image stitching. And this one is actually your CA1. Your CA1 will be on image stitching. Okay, right. So that's the whole point. We want to use this one, the key points. And when we extract the key points, we want to get the descriptors of the key points and using the descriptors to do the matching. And as a result of that, we can have this output. Right, so SIFT is the most robust features for doing this kind of matching. Key point matching is the is the things that SIFT is very, very powerful. Right, so in SIFT, there are 4 steps. One is detection of scale space extrema. The second is key point localization. The third is orientation assignment. And the fourth is the local image descriptors. So let's take a look at the first step, detection of scale space extrema. So the purpose of this first step, the goal is to identify location, correct location of the key points, and the scale of the object that can be repeatedly assigned, means have to be consistent for different images. Even though the second image is taken very far away from the object, and the first image is taken very close to the object, SIFT key points have to give you exactly the same location in the object, regardless the size, regardless the scale, and regardless the location of the object in the image. Okay, so it has to be consistent, even in the different condition. So that's the goal of the first step. So now the problem is there is a problem here in the scale space situation. So this is called scale space. So imagine that in image 1, this is your image 1, first image, and this is, for example, your second image in the extreme case, for example. That one is your second image. This is your first image. Even for this kind of situation, if you find a match or key points, for example, the key points is in this top of that branch, right? So this is called A. For this one, you also need to find, in this one, you have to find the same key point, which is called A prime. And A and A prime should indicate exactly the same location in the real world. And that's called image scaling problem. Because again, if I have an object, for example, take this pencil as the object. If I take from here, it will be very big. But if I take from far away, it will be very small. So SIFT has to be invariant or independent from this situation. Okay, that's the whole point. So that's why in SIFT, the first step is to do the image pyramids, having the images in different scale to mimic the situation that can be possible happening in the real world. Any questions here for the motivation, for the scaling down the image? Okay, so if there is no questions, in this image pyramid, we just downscale the image. Very simple, right? But theoretically that's not true. So, for example, if I show you this one, for example, the people in the nearby nearby on the from the object that I hold here, you can still see the text quite sharply, right? You can see the text quite sharply. But if I move this far away, because that's the thing that we want to mimic, if I move this far away, what do you see? It is still sharp, it can't blur. So scale space is not just scaling down the image, but it also gives you the effects of blurring. So that's also something that we want to find here. So here, aside from scaling down the image, we also need to blur the image to mimic what exactly happening in the world. So we need to do the Gaussian convolution with different size or different standard deviations of the kernel. So this is here we use Gaussian kernels. So that's why this is called Gaussian convolution. And from input image, we have to generate A, B, C, D, E here. And A, the difference between A and B is the standard deviations in your kernels. Right? The further the object, the more blurred the image will be. So that's why you have to go up to E. So we do this not only for the first scale or the original scale of the image, but also for all of the scales. So here, for all the scales that you have, you also need to blur them. So for example, here we have 7. So we have 7 stage, 1, 2, 3, 4, 5, 6, 7, right? 7 downscaling. And here we have 5. 1, 2, 3, 4, 5 different kernels. So for each size, so here for each size, so this is just one scale, you have 5 different kernels. So you have 5 different kernel A, B, C, D, E. Is it understandable? So here again is the same size. So DOG or difference of Gaussian. So this one is DOG. Difference of Gaussian operation is what is shown here. So you have a Gaussian A perhaps is very small or 0 standard deviations. You do the minus between A and B. And that gives you different Gaussian image here, 1. And if you have 5 images, 5 different kernels, then you will have 4 DOG image, 4 DOG images. So this again is called DOG images. If you do this operation, how does the DOG image look like? If you have a bit blur and a bit sharper, you do the minus operation, then what kind of output that you will get? It will give you edges, exactly. So DOG is likely to be the same as edge detection. So the operation of this will give you something like this. So this one is the different in different scale of kernels and different size. And if you do the operation of DOG for the same scale, then the edges will come out. This is again is called difference of Gaussians. Any questions here? Right. But remember that SIFT doesn't care about edges. SIFT much more into points. Try to find key points. And edges are not key points. Right. So the next operation, after we have the DOG, then we have to do the operation called local extrema detection. In this local extrema detection, assume that here you have four DOG, right? For now, let's assume that you take this tree only. Take that tree, take those 3 images, and those 3 images are this one here. Okay, so this is DOG images for different level. So now how we can find the extrema? Extrema is a point at extremum. The point at extremum, first, you have to compare this point. For example, this is the candidate of pixels that you want to see whether this is extrema or not. The first thing is that you have to look at the surrounding, 8 pixels surrounding that point. If it is extrema, either the highest or the lowest, then you take it. If it's not the highest or the lowest, you just ignore it. That's the first step. The second step, you compare that one, which is already extrema in its own image, you compare with the upper image. 9 pixels now. If it is still extrema, the highest or the lowest, you keep it. Right? You do the same for the image below that image. If it is still extrema, then that is extrema. Again, the extremum here can be positive, can be highest, to be positive, and can be negative, the minimum. Any questions here? And if this point is an extremum, then you take it as a candidate for your key point. It's called key point candidate. And if you do this operation for all pixels, for all scale, for all standard deviations, then you will have this kind of outputs. Some are positive, some are negative. Some are from the original size, some are from the very small size. Even for small size, you have to take them as key points. Right? So this is called key point candidates. Why this is called candidates? Because many of them are unstable. So now the questions, what does it mean by unstable? What does it mean by stable key points? Anyone can answer this? What does it mean by unstable key points? Remember, the whole point of this SIFT is that they have to be repeatable. So if I take the image from here and I take another image from there, the same key point have to be repeated. And that is called stable key point. Stable key point is a key point, regardless of the condition, you should be able to find the same location of the objects. Regardless the size, if I change the size, regardless the second image I take in the darker situation, I switch off the light, for example. Stable key points should give you the same key point regardless the situation that you have. Okay, so that's very important for matching, because matching is not necessarily to be the same lighting condition. Any questions here? Again, the stable key points is key points that is repeatable regardless the situation of when you take the picture of the image. Right, so now how we can find these stable key points. So this is now the second step. The first step, the goal is try to find these key point candidates using extrema operation. And once you have this candidate, the second step in SIFT is try to reject some of them, right? So there are two basic rejections. The first one, reject points with low contrast. Okay, so that is the first one, reject key points with low contrast. And second is reject points that localize along the edges. Okay, so let's learn on this one by one. Reject point with low contrast is very simple. Let's assume that you have an image. Let me see. So DOG, as you know the operation here, give you this kind of image, right? DOG give you this kind of image. And it is edges means something like this one, right? When you imagine edges, it's something like this. That's will give you edges. Or this kind of things also give you edges, right? Now, what we want to find here is edges that look like this, edges that look like this. So let's focus on that kind of edges that give you the profile of curve. Well, basically, this is not edges. This is actually corners, right? So corners or ridge. If it's ridge, it's also corner that is very long is a ridge, right? But it's kind of also pointing kind of hill or mountain, and that will be corners. So this one is the first one. We want to find corners that have high contrast. Means that we want to find corners that is high in terms of the scale. So we don't want to have hills. We want to find mountains in this DOG image. Because why we want to have mountain? Because if it is mountain, contrast is high, it is easily repeatable. Compare with hills. Hills can be caused by noise. But mountain is difficult for noise to create mountain. So mountain is something that we want to find in this first stage. In the second stage, as I mentioned, is try to remove edges because we don't like edges. Why? Because edges are not stable, are not as stable as corners. And in the end of the day, we want to find points anyway, key points, not edges. So we want to reject this one, and we want to find corners, something pinpointing that is very high contrast, very high in terms of the value in DOG image. So for this one, for the first one, the idea is very simple. The idea is that if that's the case, then have a threshold. So the green line here is a threshold. If you have a certain threshold, and if it is above the threshold, then it's a mountain. If it is below, then it's hill that you can ignore. Now, there is a problem with this. Because for extreme cases, if the mountain is very high, the contrast is very, very high, there is no problem. But in most cases, the situation is not like that. The situation is that we have many, many points that are in the middle. Somehow in the threshold of values. And we also know that noise plays an important role. Noise is always there in the image. So noise can make this hill look like mountain. Why? Because noise can be somehow add up there. So that is the situation that we have. The noise can somehow add up at the hill. So the hill somehow has a tower. It's not part of the hill, but it's just a tower made by human, and which is noise. And if you use the threshold, the green threshold, then the algorithm will deem this hill as the mountain. Okay, so now the question is that how we can identify this situation? How can identify noise add up on the value of your pixels? And that's something that we want to discuss. Any questions here for the motivation? Okay, so this is exactly what we want to identify. Actually, it is a hill, but there is a noise added up into the hill. And that's make this above the threshold. It is dangerous because you will deem that this is a strong key point, stable key point, but actually it is not. Okay, so now let's try to find this. So to find this, unfortunately, we have to go into the deep mathematical discussion. So again, the situation that we want to solve here. So imagine that you have this discrete pixel value. So I take it, actually this is 2 dimension, but let's discuss in 1 dimension first to make it easier to imagine. So this is the key point. So your key points location is there. So this is the location of your key points, right? Now, if you have a threshold and your threshold is somewhere here, for example, it will be deemed as a corner, high contrast. But if you look at the surrounding, of course, not all pixels are affected by noise. Noise is sampling randomly from Gaussian noise. So perhaps for this X location here, it is very high, but the surrounding is not necessarily to be high. The surrounding is somewhat normalized each other. I mean, the surrounding is less affected by noise. So if that's the case, that we can rely on the surrounding, because the surrounding has many pixels, right? The surrounding has 9 or 8 pixels, right? So if we believe on the surrounding 9 pixels, then based on the surrounding pixels, we can measure the exact or the predicted signals, the actual predicted signals. So we can measure somehow like this. From the surrounding, we can see that actually that's, or perhaps in this situation, the hill will be perhaps here. It's actually below the threshold. So the green histogram, the green bins are the input, the DOG input. The red line, the red curve is our output. We want to predict that signals based on the surrounding pixels. And if we can get these true signals, we know that there is a SIFT in, this is original, XO is the original, or XI is the input key point locations, but XT is actually the new location, corrected location, indicating where is actually where is the actual peak. Right? In this case, we can correct that this one is unstable key points. That's the whole concept. The question is how, from the green data, the green pixels, we can find these true signals, the red curve. All right. So let's get into the details of this. So again, the input for our operation is a patch. D is a DOG. So this one is a DOG of 3 by 3 pixels. So and the center of this 3 by 3 is actually your key point candidates. Is it clear? So again, look at here. So you have key points here, right? So take this, for example, that key points. That key points has a location. And then from that one, you take 3 by 3. And the center of that is the key points. And this one is your D. Matrix D. Any questions so far for this input? No? Okay. Okay, so with that input D, our output is a function called dx. Again, x here is the center. So D here is analog function, the red curve. Now, if we want to recover a function from a discrete data, what kind of techniques that we need to use? So from here, the matrix D, which is noisy and wrong, into D, which is an analog function, the true signals. What is the techniques that we need to use? It's called Sorry? Convolution? No. It's a mathematical operation actually. Interpolation, yeah, to some extent, yes, but it's not interpolation, it's called Taylor expansion. Well, Taylor expansion can be used for interpolation, of course, but anyway, so it is the from D into the another function we use Taylor expansion. So Taylor expansion, you know, fx, for example, in x is a one dimension, although our x is with two dimension, x and y. But let's assume here for the simple example, x is a single variable. And this one equals to fa plus f prime a, x minus a, plus f double primes, which is a second derivative, x minus a divided by 2 factorial, x minus a squared plus so on, which is a higher degree of expansion. So in this case, for the standard formulation here, fx is the unknown signals, unknown function. Right? So this one is like our D, our output. And fa here is the discrete one. So this is our input. We know this, right? Because we know A. If we know A, then and FA is given to us, then we know this this item there. So what is the meaning of this, right? Okay, so let's discuss a bit about the meaning of this, so then we can have the intuition behind. Okay, so let's assume that we have only very simple Taylor expansion, which is this one, the green box. So the green box is very simple Taylor expansion, where fx is very simplified into fa, where it means that x equals to a in this case. So what does it mean by this? It means that assume that you have a function, a very complex function, for example, something like that, and that is actually your fx that you want to find. Okay. Now, given a, for example, this is your a. The x-axis is x, of course. The y-axis is y, or fx, or y. Right. So if you know a, because if you are given a, and you are given this value there, then that's it. So you know that the location is here, and your function here, because this fa equals to, for example, a certain number, right? Because in the y-axis it gives you a certain number. Say that it is 2. In this case, your function becomes fx equals to 2. So this is for the case of x equal to a. Now, what kind of, if you have to draw this, function, what kind of drawing that you have to do? Fx equal to 2. It is a horizontal line. So in that case, it's very simple that your approximation is actually a horizontal line. That's your approximation. Your curve, your actual signal is very complex, but your approximation, because very simple approximation, is a straight line. For that particular A, it's a precise. But for the rest, here, it is very wrong, of course, because the approximation is based on one term. So now let's take a look for the second term. Let's look at the second term. The second terms will include these two. Okay, so for the second term, let's see what happened there. Fx, f of x equals to fa plus the derivative of fa, right? The derivative of fa plus multiplied by x minus a. So assume that the derivative, you are given the derivative. So the derivative is known. Function of the derivative is known. So this one is a constant, right? Constant 1. For this function here, because it's given to you, it's also a constant. It is C2, for example. And A is a constant, right? A is x equal to A. So this one is another constant. So in other words, you have a function C1 plus C2 x minus C3. What kind of function is that? Is a straight line function, linear function. So I do not know how, but it should be somehow like that, perhaps. For A, it will be very precise. Nearby A is not that wrong, but if it is far away from A, it will be very wrong. Okay. So if you continue this for the third term, so the third terms means that you include all these three. Now the function is more complex. Fx equal to Fa. I don't want to write, just you can look at that actually. But if I write down in terms of the constant, C1 plus C2 multiplied by x minus C3 plus the third terms, because the second derivative is given to you, so it has become C4, right? Divided by 2 factorial is still C4. And then multiplied by x minus C3 squared. So what kind of function is that? You have square on x, and then you have non-square, a single variable x. So what kind of function that will be? It's a quadratic function, right? The quadratic function will give you something like this. Now it is more precise, right? It is more precise compared to the straight line, more precise than the horizontal line. It means that using Taylor expansion, if you have a higher degree, then it will be exactly like your curve line, the complex curve line. And this is something that we want to use, because in the end of the day, we want to find the analog D from the discrete values of the derivatives. Any questions so far here? Yeah. Yeah, it's always tangent, but I do not know where. So take that one as an approximation, not necessarily with the correct drawing, but you get the intuition, right? You get that that should be a straight line, basically. Any other questions? No? Okay, so that's good. So this is the intuition behind why we need to use Taylor expansion. So now let's look at the exact problem that we have. The exact problem that we have is that we want to find dx, d of x, an analog function from a discrete function, and that discrete function is d when it is 0. Again, d0 means that you have 3 by 3 d, and 0 here is actually 0 bar, means that the x is 0, sorry, y is 0. Let me go like this. This is x, this is y. So the origin of this coordinate, of the red coordinates, is exactly in the middle of your 3 by 3 patch. So this one is 0, 0. So D0 refers to that location. Okay. So what is the dimensionality of this D0? What is the dimensionality here? The dimensionality will be 1 by 1. Because that's the value of that location, right? The DOG value for that particular pixels. So this is 1 by 1. Any questions? No, okay, good. So that's the first term. The second term is the derivative of d divided by, with respect to x bar, multiplied by this one, this term here, right? Multiplied by x minus a, and a equals to what? Equal to 0. So this is just multiplied by x, actually x bar. So that's the second term, the derivative of your t and dx with respect to dx. Now, what is the derivative of your dog means? So what is the meaning of this? What is the meaning of that? D dx bar equals to what? Equals to, remember the derivative. What is the derivative here means? It's a gradient, right? Image gradient, in this case, dog gradient. Dog gradient, it is a factor, right? So you have d dx, d dy. In other words, you will have dx dy. What is the definition of dx? Mathematically, what in your code? In your code, what you do? It's very simple, like what we defined previously, right? D x plus 1 comma y minus d xy. So the same as dy is equal to d xy plus 1 minus d xy. Yes. Oh yeah, that's true. I don't really have the tables. Anyone has a cable of laptop, MacBook? What's that called? USB-C. If you have a USB-C laptop, that will be very helpful because I only have one, and the other one have to connect to the computers. Mine is broken. Just today is broken, so I cannot buy it immediately. Okay, I just get for my PhD student, so it will be easier to return. Thank you. Charging. Yeah, it's charging good. Right. So, okay. So let's continue. Thanks for reminding me. Okay. So this one, dx is that definition and dy is that definition. So if you compute this for that one 3 by 3, it's doable. The problem is that what happens if you compute from 3 by 3? If you compute this one, this the one here. For this 3 by 3, what happened then? You have the boundary problem, right? You remember there is a boundary problem in the gradient operation. So if you do it locally, 3 by 3, you will have a boundary problem. So how to avoid this boundary problem then? You compute the derivative for the whole image, not just 3 by 3 of the D, but the whole DOG image that you have. If you compute this DOG whole image, the derivative in terms of X and Y, then you will not have any problem with the boundary of that pixel at least. And it's very rare to have key points at the boundary of the image. So you don't need to worry about that. Is it clear here? So you need to do the derivative for the whole DOG first. and then you take the 3 by 3 and the corresponding derivative of that 3 by 3. Is it understandable? Right. So that's the operation that you get. Then you will have this 2 by 1, right? This one is 2 by 1. This is 2 by 1 in terms of the dimensionality because it's a vector. So your x bar here, what is the dimensionality of your x bar? X bar equals to what? X bar equals to x and y. What is the dimensionality then? 2 by 1. So what is the expectation? What is the output here? The output here is a function here, right? And function for certain x, it will be 1 by 1. So the multiplication for the second term, the multiplication of the second term have to be 1 by 1. So if it's 1 by 1 and your derivative is 2 by 1, then what do? You have to transpose. You have to transpose. So then it becomes 1 by 2. And that's where the multiplication will be doable. Any questions here? That's for the second term, for the parallel extension. Now the third terms will be the second derivative here, right? And you have quadratic there. But now for this one is x here, x there is actually a scalar, 1 by 1. So 1 by 1, you square there, that's is okay, right? But now your x is actually x bar. It's not just x, but now x bar. It's a vector 2 by 1. So for that one, the quadratic of x bar, how can you make that quadratic for a vector? Yes, x transpose multiplied by x, right? So you have a quadratic function of a vector, means that you have x transpose multiplied by x here. So this one will give you quadratic. So here is 1 by 2, this is 2 by 1. So in the middle, we have these terms here, the second derivative, right? The second derivative, if you look at the second derivative of your matrix, because D is a matrix, then you have D, D here is fine, dx divided by, a small modification here, that this one is when x, so this is when x equals to, x equals to 0, 0 bar, 0, 0. Okay. So here the second derivative is that 2 square dx, 2 factorial dx bar square. When x, again, this is also the same, when x equal to 0. When x bar equal to 0. Now the question is, what the meaning of this, right? What is the meaning of that? Okay, so let's take a look at the meaning of that. So this one, the second derivative of the matrix. So D square D divided by dx bar. What will be the expectation here? What will be the dimensionality here? 2 by 2, because it's the second derivative. Okay. And this 2 by 2 equals to what? D square D divided by dx squared, right? And this one here, the other corner, d squared dy squared. So here, d squared, I don't really have space there. Anyway, so d squared dx dy, or dy dx perhaps, dx dy is fine. They're symmetric anyway, so you don't need to worry. D2 d dy dx. Right, so that's the definition of that term, the second derivative. Any questions here? So now the question is the same. How we can get the second derivative? Well, again, you have d image the whole image. You do the first derivative by subtracting the pixels in the original image. And then the second derivative, you exactly do the same, right? If you do the derivative of the derivative, then you can get the second derivative. Is that clear? If it is not clear, then I can illustrate here. So you have the whole d, the whole image d, and then you get dx. Dx is very simple, right? You do for example, that one is this one minus that one, or this one b minus a basically. Then it will give you a value here, a minus b, or b minus a. Yes, oh sorry, this one is the first derivative, not the second derivative, the first derivative. And then if you want to get the second derivative, you do the same, dxx. Now you have, this one is c, for example, this one is c, this one is d. For this location here, it will be d minus c. So c here is b minus a. So that's your second derivative in with respect to x. So what happens if it is dxy? What happens if dxy? It is a dd dx dy square. dxy, it means that you have dx now with respect to y. The second derivative is with respect to y, means that if you have e here, so if you want to decide that one, it is actually e minus c. Okay. Any question for the second derivative? Any question, anyone? Yeah, it's very simple operations. So that's how we can get all the metrics here, 2 by 2. Again, this one is 2 by 2. And this operable, operatable. So we have 1 by 2, 2 by 2, 2 by 1 is 1 by 1. So this is the operation that we need to do. Any questions? Okay, so once we have this, now remember that the goal is actually to try to find the red curve, the red curve here, right? This is the goal is to find this red curve. And in order to find the red curve, actually the red curve is not that important, because the most important thing, if you want to do the thresholding with the pink line, what is the most important information that we have to consider? Is the peak of the red curve. The peak of the red curve is the most important thing. The curve itself is not that important. Means that we want to find this xt. First, we have to find xt, the location of the peak. And then we want, if we know xt, the true location of the peak, then we can know the peak. Right? If you know the xt, then we will know that peak. So first of all, we have to find the peak, the location of the peak. How to get the location of the peak? If assuming that you know the curve line, because you already have the curve line now. The curve line is actually represented by this function here. Actually, you have this. The function here, the first term here is a value. The value there. You know this. This one, you also know that because this is the first derivative. And x, you also know x. You can just define x that you want to know, then you get x. So all the variables are known. Actually, you know the function. You actually already have the function of this red curve. Now, again, the red curve is not really important. We want to know the peak of this red curve. To know the peak, then you have to know the location. And how we can get the location of this curve? How we can know the peak of a curve? The derivative of this function equals to 0. That's right. So in other words, so to know xt, to get xt, the location of the true peak, we have to do the operation of dx, the true function, dx divided by dx bar equals to 0. Right, so now we have to operate this dx bar equals to what? So look at the first term there. If you do the derivative with respect to x bar, what will be the first term give you? It will give you 0 because it's constant. 1 by 1 value constant. So you can ignore the first term. How about the second term? With respect to x bar, what will be the value? It is only the green box term, this one. Because x will be cancelled, right? You can assume that the blocks here is actually a constant. So this one is actually a constant. The whole point here is actually constant. Constant multiplied by x bar. And then you do the derivative with respect to x bar. So the constant will be the output. Okay, so if you do the derivative of the second term, then you will have dx bar when x equals to 0. That's the first derivative of the second term. Any questions here? If you don't understand, please ask. Any questions? Again, this one is actually constant. This one is a constant value. It's a vector, right? A vector that you know the value. You can know the value here. Anyway, so that's the second term, and then the third term. The third term, if you have this square here, this x square. So x square multiplied by a constant matrix, you do the derivative with respect to x bar. So what will be the output? So you just assume that it's not a vector, but it's a scalar value. It is actually x squared, c multiplied by x squared. So what is the derivative of cx squared? 2cx. So you have 2 there. You have 2 there for the 2 factorial. You can cancel 2. right? So you cancel 2, then you will get dd squared x bar dx squared when x bar equal to 0 multiplied by x bar. Any questions here, anyone? So let's check the dimensionality. What is the dimension of the terms there? What is the dimensionality? X bar is 2 by 1, right? So and dx is a function. If you know x for 1 point, then it's a scalar value. Scalar value with respect to vector will give you the dimensionality of the vector. So this is 2 by 1. So what is the dimension of this one? What is the dimension of that one? It's the first derivative, which is gradient of your DOG. It means that for one cell, one value, one pixel is give you 2 by 1 vector. So what is the second derivative here? It is 2 by 2, right? This is 2 by 2. Multiplied by x bar, 2 by 1. So everything is correct. So now, what is the goal here? Where is the goal? This one is equal to 0, right? This one equal to 0. What is the goal here? To find what? To find x. 2 by 1 x there. That's something that we want to find. So x bar star, which is the optimum one, equals to what then? Equals to minus d square dx bar square when x equal to 0 inverse, correct? Multiplied by dx bar dx bar when x equal to 0. That's it. That's the location of your true signals. From DOG, you will know this one. You know this one. From DOG, you also know that one. The first term is the second derivative. The second term is actually the first derivative of your DOG. Any questions? Yes.
Why do we use only the second derivative?
Yeah, this is a good question. Actually, as you can see in the explanation before, I'm not really sure where, this one, for example, right? If you go further to the higher degree, of course, it's more accurate. But the inventor of this SIFT decided that up to the degree of 2, order of 2 is sufficient. Yeah. So this is kind of approximation, of course. Why? Because the peak, if you want to find the peak, right? If you want to find the peak, it's actually quadratic will be sufficient. So this one, again, where is that? So as long as it's square, that one is also good enough. Anyway, so you know what I mean here. All right, good questions. Any other questions? Any other question, anyone? So again, this x bar or x bar star is actually xt, the true signal location. So what does it mean by this true signal location? This true signal location again refers to the 3 by 3 DOG patch. So you have the discrete version DOG patch. So you have this 3 by 3, and x bar, when x bar, let's see, when x bar equals to 0, 0, what does it mean by this? Where is that? When x bar equal to 0, 0? Anyone? It is exactly in the middle of your patch. So this one is when x bar equals to 0, 0. Now, when you have x bar star, the true location, if the magnitude of this greater than 0.5, where it will be. So this one exactly in the middle is 0, 0. 0.5 is actually referring to this one. This is 0.5. Not really necessary. Either that one or let me see. The magnitude of 0.5, I think is this one. 0.5. Right? So basically anything larger than 0.5, it will go beyond that particular pixels. So it will go beyond particular pixels in either this one, that one, this one, or the surrounding pixel, basically. And that's the location that we want to get from this X star. So if the offset of the magnitude of X star greater than 0.5, then we move the peak, we move the location of the peak. It means that we know that there is a SIFT. There is a SIFT of the peak, means that the original one is wrong if the magnitude is greater than 0.5. Okay, so now what do we do next? If it is shifted, so we know that now it is shifted to the next one, for example, then the next step is to test whether this one greater or not compared to the threshold. So the second step is to compare with the threshold. So we have a new location, D. So if it is greater than 0.5, so if then test that D X bar whether or not this one, the magnitude of this, the absolute value, because D can be negative, right? They can be negative, can be extremum, or can be maximum. So if this magnitude, the absolute value of this is smaller than 0.03, then reject. So why the 0.03? By the way, 0.03 is a threshold decided by the inventor of the SIFT. And 0.03 here refers to the value of D, I think 0 to 1. The optimum value of D is 0 to 1. Either D or input image is 0 to 1. I'm not really sure. Please check that in the paper. I forget actually which one is which. But anyway, 0.3 here have some assumption that the value of the input image is either 0 to 1 or D value, the range of D value is between 0 to 1. But it doesn't really matter because this one is decided by human anyway. As long as consistent is fine. The question is how we can get this value here. Obviously, you can just use this one, right? To get the value, you can get this one. Go back to this equation, and then you can get the value of D. Any questions? Yeah.
So the test of the dx star is using the continuous function.
Yeah. Yeah. So you get this D value here, the value here from this one, from this equation.
So using the pixel value of the nearest.
Oh, this nearest one is already, this one is X star. The true X, because in the end of the day, we want to find the curve line, right? So now we have this one, XD, X star. Then we want to know the peak, right? That this one, the red line here is actually, the red line function here is dx. So we have to use the definition of dx here to get the peak, the value of the peak. Right. Any other questions? Yes.
We need to find a new key for every patch. And
For every patch, but remember that we are dealing with key points here. So not all pixels, but only the one that have the value here, the plus and the minus. Only the plus and the minus location. Yeah. Good questions. I forgot to mention this. Any other questions?
so we only talking about grayscale.
That's correct. We only DOG is actually grayscale, and also, yeah, I didn't explain this in the beginning. This SIFT is really only dealing with grayscale images, grayscale input. Okay. There is a SIFT for color, but it's not that useful. Yeah, good questions. Any other questions? So how many of you think that it's too complicated? This operation to find the peak, to find the rejection. In the end of the day, we just want to reject these points, right? And that's how we reject. We reject the one that is below the threshold. How many of you think that it's very complicated just to do the rejection? Yes, many people think that it's complicated and it is take time. The operation of SIFT is not real time because of many operations that we are doing here. That's the weakness of SIFT, but don't blame me. Blame the inventor of SIFT. So it's not my invention. So if you look SIFT, SIFT, right? SIFT. Descriptor. So this one is actually invented by this guy, David Lloyd. So blame this guy for making things complicated. But if you look at the Google Scholar, so David Lloyd, right? So SIFT is number one there. Distinctive image feature from scales image in key points. This is cited 67,000 times, 67,000 times. So it's a landmark of a paper. Even Viola Jones is not reaching this number. Anyway, so yeah, that's the first step or the second step actually. And before we continue, let's have a break. Let's start the second session 10 minutes past 8. Let's have a break again.
What is this item? It's just the direction.
The coordinates. The coordinates, when I x equal to 0, 0, you do not know where the coordinate is, right? So 0, 0, the coordinate of the
Middle. So the y and x is just the
axis.
sense. Just the orientation.
No, the orientation. This one is 0, 0. Means that the upper one here is 0, 1. The bottom one here means 0 minus 1.
Oh, okay.
So this is indicating the coordinates.
Something that is defined by the inlet.
Yes. Well, the 0.5 is because of the coordinates here, right?
Yeah, but why it's not 0.5 multiply the square roots 2? I think because if I'm in a corner, there should be
I'm not, yeah, that's a good question. So basically, this is 0, 0, right?
yes.
And this one, I think it's a 1, 0. And
Yeah.
this one is 1, 1.
Yes. Sorry, I think this one should be
So it's 1,
0,
0,
1.
1.
Yes. Yeah.
Offsets means that x plus y
Yes. Square.
square have to be greater than 0.5.
Yeah.
Let's see that if it is 0.5 plus 0.5, which is here, right?
Yes.
Square. What is that?
0.5
0.5
multiply
plus 2, right?
square root 2.
Which is 0.5.
Yeah.
It is actually 0.25.
Oh, what?
Okay. What is the square root of 0.5?
I think it should be 0.5 multiple square root 2.
This one correct, right? So
Yes.
this one correct, right?
Yes.
This one is correct, right?
Yes.
So what is the square root of 0.5?
0.5 multiply by square root 2. And I go switch to this one.
Yeah, what is that? What's the value there?
Equals to, oh, it's smaller.
So 0.5 means that even the longest one, it gives you the location, the next pixel
Oh,
already.
sorry.
Yeah.
We have 5. If we have 4 DOG in the slide, and we need to find the key. We need to find the key points, and we need to compare it. So here, we need to compare it to the top
and the
one
bottom.
and the bottom one.
Yeah.
But we have 4, and
You have to do it multiple times.
what about the top?
Don't care about
The
that.
top and the bottom.
Don't care.
We only care about
The
the
middle
middle
one.
two.
Yes.
Okay.
Sorry, I think it's 0.7. 7.
I do not know what exactly that, but
May I borrow that? Where is that? Because the square root 2 should be 1.41414, and then this one should be 0.7. 07. So it's larger than 0.5. So
yeah, you can use the 0.7 if you want.
okay,
It doesn't really matter.
So it's
Just
the
basically-
offset I can.
Yeah.
The scaling down, you say that when we do the operation below, then we only focus on one scale. For example, it is the original image scale. Then we do the Gaussian convolution and the key point organization below. Then what about the scale? The scale
You have to do
we just do if we
exactly the same operation. So for this scale here, you have to exactly do the same operation.
do the same operation.
Even for the smallest one, you have
Okay.
to do the same operation. So in the end, you will have these points for all scales.
So these key points is not just the
Not the
scale,
original one, not the original scale, but it's for all scale.
for all scale.
Yeah.
So when we do this operation, we don't need to match the key points.
Not yet. You don't need to match.
Okay.
You don't.
So
But you keep the whole information of different scale. You know where that this key point is generated by that scale. You have to keep the information.
okay. Thank you.
Yeah.
Here is for last week lecture. So let's say if you want to get some of this 4 points,
Yeah.
and then it's this.
The blue one refers to the blue.
But if you want to
circles.
go get the sum of the whole image,
Then you have to put the point here.
but there won't be any.
And that will be 0.
Oh, This one will be 0. And this
It's
for top-
0. Yeah.
Oh. So for the because for there's one that is we increase the mask by 1.7 times. Then we will upscale
Yeah.
also,
We ups-
but we won't stop at 24 times 24.
So upscaling 1 point, for example, if you upscale 1.7 for original mask, right?
So 24 also upscale by.
So the 24 by 24 have to be upscale up to by 1.7. If you want to get that as, because you don't have that one. I mean, 24, you don't really need to have 24, 20 right there, because you trust your mask to give you the descriptors.
So we upscale by the same number of times.
Yeah, so then you can have a descriptors. You don't really care about the input image anyway.
Okay.
Yeah.
And for James, the project also at the end is if let's say the norm is more than 0.5,
Yeah.
we think that's not the mid one. So it's the one.
Yeah,
Well,
the one is surrounding.
So we have to recompute the D,
You don't, which D, the analog one or the discrete one?
this.
The discrete one cannot change because it's already the input, right? The DOG input. The discrete one, the matrix is given to us.
You know D of X star.
The one is the analog one, right? The function, the analog is analog means this red curve is analog, right? This red curve here is analog. The discrete one, the green one is the discrete one is DOG.
So the final, if let's say it's not the middle one, then we need to compute a new.
So this one is shifted.
Uh-huh.
Shifted 1 pixel, for example, into XT star. Then we need to find the peak of that location, right? Because we know that it's shifted already. So we want to know the peak value. And the peak value is that you know this one already. And then you just insert that there. And then you know the function D already. Yeah. 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 So that's right. So yeah. So here, actually, the value perhaps is perhaps is here.
Yeah, but it could be noise, yes.
Yeah. So then the green here It's the noise.
And because of this, it is crossing threshold and
Yes,
considering it.
that's correct.
Okay, so now my question was,
Mm.
so because of this curve,
Mhm.
we are able to get the truth
Real,
maxima
yeah.
and we are able to consider it.
Yeah.
So, first of all, this second order is a very approximate Taylor function,
Yeah.
right?
So this one is the blue one. So the approximate
Yes, yes,
is the blue one
yes,
here,
yes.
the blue line, yeah.
So, is there a possibility that suppose there was no noise and I mean, there was a noise, but it was very little and as getting a curve. But because of this approximation, the new maxima I got, which was below the threshold, and I lost the point.
Yeah, but that you don't actually to worry because this key points is actually have to be rejected anyway because it's unstable. If it's something that approaching the threshold, this is very unstable.
So, is there also second question?
Hmm.
So, is there also a threshold on both the sides, like on the minima side also?
Oh yeah, you have to make an absolute value. So
Okay.
that's why I put it absolute value here.
Okay. Okay. Okay.
Hmm.
Okay.
All right, so let's start the second session. Oh, by the way, some of you asked about this drawing here, right? So just want to make sure that you understand what I mean by 0, 0 here. So this is x and y are the coordinates, the axis. So you can imagine that the middle point here is 0, 0, right? So again, the middle point here is the coordinate when it's 0, 0. And this one, the x-axis, if it is 1, then it's 1, 0. And that one is 0, 1. And perhaps something here, somewhere here is 1, 1. Right? So that's the coordinates. Specific x and y are the coordinates. Okay, anyway, so now let's get back into the idea of this one, right? So we already evaluate number 1. So we already anticipate that there is a noise. So a noise here, to be more definite, in my previous drawing, that xi is the actual location. So this one again is the actual location, not actual location, the location given to you by the first step in SIFT. And that one is suffer from noise. So the green on the top here, the green on the top is the noise. If there is no noise, then you only have the red things there, right? So in other words, if you use the threshold for the pink line, then because of the noise, then it will be accepted as a stability point, but actually it is not stable, right? Okay, so just want to make sure that you understand this number 1. And number 1 is focus on corners. So the assumption there, the key points that whatever you get from this operation here, so the operation here is assumed that the key points is the peak of a corner. And then we do the rejection based on the contrast. And the second point here, sometimes or in many times, the supposedly corners point, key points here, also lies on edges. So for example, I can give you, this maybe not really true perhaps, but if you focus on that, if you focus on this, right, this area here, it might not be a corner because that's is actually the line. Of course, I cannot see the lower scale, because maybe in the lower scale that is a corner, or maybe in the different Gaussian blurring that is a corner there. I do not know. But if we just believe that this is the DOG, then it is not a corner. That's an edge actually. So anyway, so in many cases, according to David Law, that this one perhaps not perhaps, but many of the key points are actually lies on the corners. So we want to reject lies on the edges. I mean, so we want to reject key points that lies on edges. Right. So based on that, the second step in the second sub-step in the second step is actually what is that called? Edge detection, edge rejection. So the second step, the second sub-step in the second step is edge key point rejection, key point detection and rejection. So the basic idea is based on a very simple principle, very simple idea, that if you have a point distributions, so imagine that if you have a point distributions, then you can measure the first principle and the second principle components. right? So where will be the first principal components? Anyone? Where will be the first principal components? They'll be aligned in the direction of the distributions. So this is the first principal component. And where is the second principal component? The one that is perpendicular to this line. And that one is this one, perhaps. And that one is V2. So how can you get V1 and V2, by the way? Using eigenvectors and eigenvalues. So basically, V1 and V2 are eigenvectors and eigenvalues. Oh, sorry, V1 and V2 are the eigenvectors. The first eigenvectors and the first eigenvectors and the second eigenvectors. If you have eigenvectors, you always have eigenvalues. So the eigenvalues for V1, for example, represented by alpha, for example, this alpha, and the second eigenvalue will be beta. So alpha and beta is actually the magnitude of this vector, indicating the magnitude of the vector. If the eigenvalue is largest, I mean, then it will be the most important principal components. Anyway, so if you have two-dimensionality of distribution of data, you have V1 and V2. And because V1 is the principal components, then alpha greater than beta. So now, intuitively, what will be a corner? What will be the condition of a corner? And what will be the condition of an edge? What will be the corner distribution look like? It will be a circle, right? If it's a circle, what happened with alpha and beta? They are the same. So alpha equal to beta, indicating that it is corner. Is alpha greater than beta, much larger, then it will be edges. So that's basically the idea. Through alpha and beta, the correlation between alpha and beta, we will be able to judge whether the distribution of points are edges or corners. Any questions here? So if this one is the distribution, for example, in the space of X and Y, and if we have another space, let's say that if you have a space of alpha and beta, then where will be corners in this space? Where will be corners in this space? When alpha equals to beta, which is somehow in this line here. But you cannot use this one. You cannot use there. Why is there? Why cannot we use the one that is below the line, the red line? Because alpha and beta are too small. If alpha and beta are too small, means actually the supporting points is not that strong. This can be just noise. So not only that we want to find alpha and beta that is very similar, but we also want to relax them. Just try to find a sweet spot when the difference is actually tolerable. So in the end, we just want to have this as the indication of corners. And the rest are edges. Okay? Any questions here? So now the question is that how, given only the input, remember the input is only D, and D is only 3 by 3. we don't really have that many pixels. To get the PCA or eigenvalue and eigenvectors values, you need to have a lot of data. In this case, the points here. If you have a lot of points, that you can have alpha and beta. But in any case, of course, if you have small alpha and small points, small distribution, you can also have alpha and beta. But the point here is that the absolute value of alpha and beta is not really important. The most important thing is the ratio between alpha and beta. If we know the ratio of alpha and beta, we know whether this is corner or edges. In any case, our input is D, the DOG, where this one is the middle here is the key points. Okay. Now, to get this into this idea, we need to know the value of alpha and beta. The question is that finding alpha and beta, if you do the operation of PCA or any eigenvectors computation, it will be too slow. So to speed up the process, there's a few steps here that we can do. The first one is to compute Hessian matrix. So remember that the input is always D, 3 by 3 pixels. First, we want to find or compute a Hessian matrix from D. So Hessian matrix is H, and H here is, what is the definition of Hessian matrix? What is Hessian matrix? Hessian matrix is the second derivative of your matrix. So that's Hessian matrix. So Hessian matrix is the second derivative of your value that have two-dimensionality. If you have two-dimensional data, the second derivative of this two-dimensional data is a Hessian matrix. So anyway, so you have D, the derivative of D. So I can just write here, Hessian matrix is dxx, dxx, dxy, dyx, dyy. So how can we get this Hessian matrix? Well, actually, we already have this one because in the previous edition we have that, right? By having that means that we have a Hessian matrix. So we can just reuse whatever we had in the previous calculation, in the previous step. Any questions here? So for every pixels, we can have the Hessian matrix. Yes. Yeah, we do not know yet. That's the whole point here. The goal is try to find the ratio or to find the somehow correlation between alpha and beta. What do you mean by useful information?
The colony, the key colony you have. Yeah, like if you've chosen this key one, they are useless because it is better at the corner. But how can we catch that it is in that useless colony?
So I'm not sure your questions, but I can just give you the information that edges are not stable. Corner is more stable than edges. Is that understandable, Buzz? That corners are more stable than edges. Why is that? Yeah, we find the key points because in the end of the day, we want to find key points, right? Key points is more repeatable if we can find corners. Texture corners means that, you know, you have very textures trash here. So the corners means that corners of the texture. And that corners is more stable. Why? There are many reasons. For example, obvious things is like hard shadow, for example. It can give you line. hard shadow. You know hard shadow? So I'm not sure if I put this one, if you, I don't know. So let's put this light here, right? So I'm not sure if you see that one, the shadow there. It is called hard shadow because it's very sharp. And this hard shadow, if your key points based on the corner, sorry, based on the edges, it can give you some edges here, right? But it's actually not repeatable because if I don't have the light, the shadow will be gone, and you can get trapped into the edges, right? So edges are not stable. One of the reasons is because hard shadows, but there are many other reasons as well. Okay, so that's one thing, that corners are more repeatable, more invariant to lighting and to other conditions. So that's why we don't really like edges. We like corners better. Okay, yeah, good question. So there's an opportunity for me to explain the difference between corner and edges. Any other questions? Okay, so yeah, basically we want to get the corners, and the operation here is first we have to find the Hessian matrix. The second step is that we want to find the trace of this Hessian. What is the trace here? What is the trace of this H? Can anyone say it here? Dxx plus dyy. And I don't really want to prove here, but you can look at Wikipedia or something like that, that this one equals to alpha plus beta. So there is a correlation between the trace of the Hessian and the eigenvalues. That is the trace, and the determinant of H equals to what? If you have to compute the determinant of this 2 by 2 matrix, equals to dxx multiplied by dyy minus dxy multiplied by dyx, which is a symmetric matrix. Hessian matrix is a symmetric matrix. Because it's symmetric matrix, then you can just square it. Okay, so this is called determinant. And this determinant equals to alpha multiplied by beta. Okay, so now the third step, if you put the trace square H divided by determinant of H equals to what then? Alpha plus beta square divided by alpha beta. And let's define the correlation between alpha and beta is R multiplied by beta. So this is, let's assume in this way. We do not know R, but there must be some R, some value of R that makes this equation hold. Now, then we have, if you use R, then you can have R plus 1 squared divided by R. Correct? Now, based on this, then we can do some verification. If alpha equals to beta, then R equal to what? 1. If R equals to 1, then the value of the ratio trace of H divided by determinant of H equals to 4. So if it's really corners, very, very perfect, then the trace divided by the determinant equals to 4. And if alpha equal to 2 beta, R equal to 2, the trace square divided by determinant equals to 4.5. If alpha equal to 10 beta, R equal to 10, trace square divided determinant equals to 12.1. So this is the idea here. Of course, this is again based on human observation. So this one, if hence, if the threshold, the trace divided by determinant, the trace square divided by determinant smaller than 12.1, then retain. Otherwise, reject. So this one is assumed to be H. Any questions, anyone? So basically, that's the idea how we can get the corners to know the ratio between alpha and beta. Any questions? No questions? So I assume that you know this. All right, so if you know this, then let's move on. So this is how you can recheck the key points. So that's number 2 there. So the number 2 here, if it is edges, then you recheck based on the ratio between the trace square divided by the determinant. So with that, we have done this, right? We understand this now. And oh, by the way, as you can see here, x hat is actually the new x location, and they compute this one is in a very simple way, not even including the third terms. So in the paper, so in my explanation, actually I use all the terms here to get d. So all the terms here, complete them under the third order. But in the paper, it's actually just use the 2 to compute the d, which is a more approximation. But again, I cannot say anything on this because this is decided by the inventor. The inventor prefer to use this one, not up to the third terms. But anyway, this is just a small note in case if you are wondering later. But this one, the second one, step B here, H elimination, we already understand this. This is based on the 3 steps. And yeah, I already explained the intuition behind. Now, that's the key point localization, key point filtering. We just want to remove many key points, many unstable key points. And supposedly, the image on the right is containing the key points, stable key points. Okay, so now that's the end of the second step in SIFT. The next step is orientation assignment. So the orientation, the idea is very simple. You know, when you have an object like this pencil, for example, this pencil can be taken. If you take a picture, you can take a picture in this way, but you can also take a picture in this way. You can take a picture in any different rotation. So the same in human face, for example, it can rotate as well. In many different objects, it also can easily happen that the rotation in many different images. So now how we can deal with this rotation, right? The idea is that we want to transform from the image into canonical orientation. Canonical means standard. So canonical here means standard orientation. And this standard orientation is this one, when the maximum, so this is actually the maximum gradient. most dominant gradient. So this is the most dominant gradient. We want to make the most dominant gradient always horizontal, regardless the input image. First, in the image space, if it happen that this one is the point here is your key points, if that happen to be your key points, then you crop the image of that surrounding the key points, and then you rotate this into the canonical standard orientation, where the dominant orientation have to be horizontal. Now, regardless your input here, the orientation of your input, you have to transform this into the canonical standard orientation. Any questions here for the intuition behind the operation? Okay, so now how we can decide this dominant orientation, right? How can we know the dominant orientation? Oh, by the way, we don't deal with DOG anymore. We're dealing here in the third step with the input image, the original input image. But you have to be careful here. There is a big square and small square, right? So what does it mean by small square and big square? Anyone? The smallest that you can find is this one. That's the smallest. Around the eye. So what is smallest represents? The smallest represents the original scale of your input. That's the largest input that you have, the largest scales that you have. And that gives you the smallest square. And the largest square that you can see is this one. This is the largest square. And the middle of that is actually there. So what is this represents from? It is taken from the smallest scale. Because you have to downscale the image, right? In the smallest scale. And the smallest scale gives you these key points. This gives you X key point. And again, in that scale, in the small scale, you have to crop. I think it's 32 by 32. So this one, the square here is a 32 by 32. Any questions here? Okay, so the input, again, once we have X, the key points in any scale, we crop 32 by 32. And that's the input of this operation. Right, so now it's a simple things. You have to compute. This one is 32 by 32. I think 32. Sometimes it's 16 by 16. But regardless, 16 by 16 or 32 by 32, it doesn't really matter. As the important thing is that you have these key points in the middle and the surrounding pixels. The same as in HOG, we need to compute the orientation for each of these pixels. And we also need to compute the magnitude. So orientation and magnitude. Then this is the description, the depiction of the orientation. So this one here, showing the magnitude of that particular image or patch. And the bottom one represents the gradients, the most gradients. So not the most dominant gradient, but actually the gradient for each pixels. And then here you have to create a histogram. The histogram has 36 buckets or 36 pins. So it's not 8, but 36. Means that the range of one pin is what? 10 degree. 0 to 10, 0 to 9, 10 to 19, 20 to 29, and so on. Okay, so based on this histogram for that 32 by 32 or 16 by 16, then we will have a histogram. This is the histogram. How many of these? How many bins? 36 bins. So based on this, then you will find the peak. So this is the peak. Once you have this peak, then you have to shift this peak into the y-axis. By having this shifted, how about the value here then? The value here will go to the end of the histogram. So you shifted everything. And the one that is on the left, you have to put on the most right. Is it clear? Any questions here? So this one, once you have the red line coincide with the y-axis, that's the canonical orientation. That is the horizontal line, because that one is horizontal, means 0 degree. And the most left, or the most, I mean, if this coincides with the y-axis, the pin is 0 degree, right? So that's why it is a horizontal line. Any questions here? Okay, so this is how you can make the histogram, or sorry, make the key points, the descriptor that you will have later on, to be orientation invariant orientation, independent from rotation. Small things there, small things here. You know, instead of finding the peak, the algorithm actually said that it is within the 80% of the highest peak. So it means that this one is there is a threshold there, and if it is above the threshold, you take that as the peak. Now the question is that what happens if you have two that above the threshold? If you have two above the threshold, then you have two different orientations. So you have one here and two here. So for that particular, although you have one key points, then you have two key points. One is representing number 1 and the other is representing number 2. So there will be two images that you have to keep for that one key point. Is that understandable? So in other words, the key points in terms of the orientations are not unique. So one key point can have two different or three different orientations. Anyway, so just keep that in mind. Now, the last operation is this local image descriptors. So we need to create a descriptors. So the last one, so assume from the previous step, we already have a canonical orientation. So the I here already like that, right? And the orientation is in that way. The dominant orientation is already normalized. Now, if we assume that this is a 32 by 32, for example, so assume that this patch is 32 by 32. Then the next operation is that take the middle one, I'm not sure the middle one is this, perhaps that one, is the location of your key points. For the last operation, you only need to have 16 by 16. So this one is now 16 by 16. So it's just part of the patch. If your previous patch is 32 by 32. If your previous patch is 16 by 16, then that's fine. You don't need to do anything. The last one is 16 by 16. So we have 16 by 16 now. So assume that it's 16 by 16. And this 16 by 16, then we have to divide into 4 areas. If you have to divide into 4 area, one area here, what will be the resolution of one area? It will be 8 by 8. And this 8 by 8 is what is described here. So this one is 8 by 8 pixels. Okay, so from 16 by 16, we focus on 8 by 8. So let's take a look at this 8 by 8. So this one is 8 by 8. In 8 by 8, we split again into 4 by 4. So you split this again into 4 by 4. So here we have 4 by 4. So for this 4 by 4, you know the orientation and the magnitude. And for this 4 by 4, which is 16 pixels, you create your histogram, your oriented histogram. So that's why this 4 by 4 give you 4 by 4 here, give you that one. Okay, so that one is created by 4 by 4. And we only have how many pins? On how many? 8 pins. So for 4 by 4, you will have 8 pins, 8 values, or 8 pins. That is for this one. For the second one, you will also create a histogram. So for the second one, you also create a histogram. How many pins are there? It's also 8 pins. All right, so you do the same for all the areas there. So for this 8 by 8, for this 8 by 8, if you have to create a histogram, what is the length of your histogram? For this 8 by 8, what is the length of your histogram? 8 by 4. If you have to combine all this operation here, 8 by 4 by 4 equals to 128. And 128 is the length of your SIFT descriptors. So this one is your SIFT descriptors. So when we talk about SIFT descriptors, it's taken from 16 by 16 patch surrounding your key points. And it is the representation of your normalized oriented patch, because you already rotate the patch into the canonical standard orientation. And you have to do this for every single key points. Any questions? Any questions, anyone? So in the end, you will have this. That will be your key points descriptors, the visualization of your descriptors. Oh, by the way, you have to do this. This is one of the one that in the assignment. Well, you don't need to do all the mathematical things. That's the good things. You can use whatever package there in the internet. You can just use a package of SIFT. I will let you know later on using OpenCV, and you can just show this and several tasks that you need to do to get the information, to get your understanding. Anyway, so this one, as I mentioned, there will be there will be a assignment. And the assignment is based on SIFT. And what you do is to do this image stitching. So the next week, we will get into this image stitching algorithms. Okay. Right. Any questions, anyone? Any questions? Yes.
For the average solution, how do you deal with like the scale environment?
Yeah.
In the demo, so like how to apply
What invariant?
apply environment.
Affine invariant. So yeah, that's a good question. How this can deal with affine invariant? So affine invariant is the one that is shown here actually. So this one is called affine invariant, right? So affine invariance, again, if you just look at your edges, it can be wrong. So edges is this one. The information of edges will include this part here. And that one, if you compare with this one, if you take the gradient profile of this patch and that patch, it can be different. That's the danger of edges, because the gradient profile of that patch will be different. But if you take corners and get the same kind of location here, it will be more robust. Although they're still different, not really 100% the same, but that corner's gradient or orientation is more robust than the edge gradient orientation. So we don't really, of course, the affine here is up to a certain angle. If it is above 90 degrees, so for example, if you have an object like this, you take from that one in one image, and then you take that another one in the other image, it's of 90 degrees already, it will fail. But if it is just before 60 degrees, it's still okay. In the experiment, it shows that it's robust to 60-degree orientation. Yeah. Any other questions? Okay. All right. Any other question, anyone? All right. So I hope that you learned something today, and I will discuss with you again next week. Thank you, everyone. Thanks.